Hello everyone, welcome to the second lecture of this week. We have one more fundamental topic to cover in the Pandas notebook, and then we'll be moving on to an example of data munging, which I'll explain more when we get there. So often we will want to work with multiple data sets at a time. So for example, we have in this notebook been working extensively with a data set from Yelp. But we might additionally want to know some characteristics, geographic, demographic characteristics of the cities in our data set. So I've loaded in a second table here, where we have a bunch of different cities in the United States. Here it's just showing Connecticut, but we have cities all over the United States in this data set. And we have the populations for each city in, I guess, July of different years. So this will help us put into perspective, for instance, how many reviews each business has in our data set. Because obviously, in larger cities, businesses will be prone to having more reviews. So we might want to work with these two data sets together, but currently they're in different tables, and we'll need to somehow bring them together and put them in correspondence with each other to match up the rows of one table with another. So for this census data with the populations of the different cities, we have a field that contains the names of these cities, but it's different than the format in the Yelp data. So in the Yelp data, we have just the city name. We also have the state abbreviation here in the full address. Actually we have a state column as well. So we'll probably want to extract from this geo display label the name of the city and the name of the state. So we'll construct those two fields. How will we do it? Well, let's just take the first entry in that column as an example and think about how we might do it. So we can see there's a recurring format among all these names. We have the name of the city, comma, the county, comma, the state. So if we split up these strings by commas, or comma space, then we end up with three pieces: the city, the county, the state. The third element will always be the state. The first element we'll call the city. So we could define a function that takes some string s or place string, and returns let's do it this way. Place list equals place string dot split returns the city, element 0, and the state, element 2. And then, if we had we could take this column and apply this, oops, I'm not sure how far I was zoomed in before. This looks like too much. I think it was this way. Okay, we can take the display labels and apply this parse place method, and we will get back Betheltown, Connecticut, Dariontown, Connecticut, all these cities and states. Now, I'm going to do it in a slightly different way, using what's called a lambda function or an anonymous function. So I've shown these before, I believe, but I don't think we've made use of them very often. But in Pandas with apply, they become much more common. And you'll see me using them a lot. So the way a lambda function works is instead of define, we have lambda. That's like our define statement. You can see they're both highlighted in green. We don't have a name for the function because this function is anonymous. It has no name, which means that it doesn't stick around in our namespace, and that name is, or the function gets garbage collected later. And this is good when we're going to use a function just one time and then never use it again. We kind of want to use it and then throw it away. So that's one of the reasons lambda functions are very common with Pandas, is because we'll often use a function just once to transform a column or something like that. Then we have the name of our argument. So before I name the argument place string, here I'm just going to name it x, which is not very descriptive. Maybe I'll use s instead, at least to indicate that I expect this to be a string. And then I have what the function should return. And I want it to return, in the case of the city, I want to split the string by comma space and return the first element of the list. In the case of the state, I want to return the third element of the list. So now I have the states from my census data. We can see this is not a complete census data set. These are only some of the states in the United States. And another problem is here we have state names, but in the Yelp data set, we have state abbreviations. So I'm going to construct a dictionary with these state names and their abbreviations. And then I'm going to use the replace method which will take this dictionary and simply map the state column. It's essentially going to use this dictionary to map the entries of the state column to the values in the dictionary. So now this column has abbreviations. And then finally, in the city column, all of our cities have town or village or city at the end of the names. So I'm going to remove the last word from each city name. So I could take a string like Bethel town, or even say Las Vegas city. I could split that on spaces. I could take everything in that list except for the last word, and then I could join those together using spaces. So I put all of this into a lambda function, but instead of Las Vegas City, I allow myself some kind of argument, S, whatever the city name happens to be. So I have the argument S, and I take that and I split it on spaces. I take everything except the last word, and then rejoin that list together into a string using spaces. So join and split are mirror images of each other. So now my city names look more like I would expect them to be. So now if I compare the state and city columns of the census table, they look pretty similar to the city and state columns of the Yelp table. So I'm ready now to join these tables together. And I can perform joins in a number of different ways in Pandas. There's extensive documentation with diagrammed examples on different methods for joining data. Once again, this documentation is very good. You can see there's diagrams with example code. But one of the most common ways to perform a join in Pandas is to use the merge method. So I'm going to merge these tables together, Yelp DF, and I'm merging in the census table, and I'm going to specify that I'm merging on state and city. So the merge function is going to look through state and city of both tables, Yelp, DF, and census, and match up rows that share values for state and city. So for example, for Middleton, where did state go? Oh, it's in this ... but it's Wisconsin. So Middleton, Wisconsin. Here we have our geo display label, Middleton City, Wisconsin, and we have all of our census data. So where the Pandas was able to find a match on city and state between the two tables it concatenated the columns of the census table to the columns of the Yelp table. And we can see this doesn't always result in exactly what we want. So we have to be a little bit careful. So here we have duplicated data. So we have the same business twice. We see it has the same business ID because a match was found on Middleton, Wisconsin. And there is apparently a Middleton city as well as a Middleton town. And remember, I got rid of city and town in our census data. So this is something I hadn't noticed before. This is actually the first time I've noticed this. But it's something to be careful about. Is if you get multiple matches, you might duplicate data that you are not planning to duplicate. The census data is different, but the Yelp data is the same. And of course, in many cases, my census data is the same, so I have multiple matches for Middleton, but the Yelp data is different. And that we would expect, right? There's many businesses in a given city, so we would expect this census data to be repeated quite a few times. Not so surprising. Now, I've shown what happens when a match is found, and we've even talked about what happens when multiple matches are found. But what happens when no match is found? There's 4 different scenarios we can imagine. We only keep rows when a match is found, and if there are rows in the Yelp data frame that don't match with anything in the census data frame, or rows in the census data frame that don't match with anything in the Yelp data frame, then we just throw those rows away. And this is what's called an inner join, where we only keep the shared content between them, the intersection. If you imagine a Venn diagram, which I don't have a picture of, unfortunately. Maybe I do in another notebook. Let me check real quick. No. That's too bad. So if I had a Venn diagram, the inner join would be the overlap. Oh, maybe I have a diagram in this for intersection for sets. Yes, okay. So the inner join is if I have like table A and table B, and they match on a certain subset of their elements. I keep only the pieces that match. So any businesses for which I don't have census data get thrown away. Any towns where I have census data but where I have no business data also gets thrown away. Another thing I can imagine is I keep all the records from the Yelp table, no matter whether they match or not. Where there's no match, I just have missing census data. So I fill it in with nones or nulls. And I could likewise do that for everything in B. This would be like a union, where we keep everything. So we keep all the rows from both tables, even if they have no match. When a row in the Yelp table has no match, all the columns from census are merged in with null values. Basically, I have businesses where I don't have census data, I just have missing data there. So I keep the row, I concatenate all the columns, but I put null values, and vice versa. So this is called an outer join, and that's like a union. I keep everything. And then the other two joins are called left and right, where we privilege one data set or another. So for a left join, left because Yelp DF appears on the left of this merge, census appears on the right. So on a left join, if a business has no census data, we keep that business and fill in the missing census columns as nulls. However, towns where we have census data, but there's no business data in the Yelp data frame, we throw those towns away. We discard it. So that's a left join. And the opposite is a right join. Same idea where we swap Yelp DF and census in the description in number 3. So the default behavior in Pandas is the inner join. If we don't say how we want the join to be performed, it will do an inner join. So in fact, if we look at the shape of merged DF, it has less rows than both the Yelp data frame and the census data frame, because we only kept rows where there were matches, so we have less rows than either of them. If we did a left join, we would have as many rows as are in the Yelp data frame. If we did a right join, we would have as many rows as in the census data frame, or possibly even more, actually. So that's also here. We can specify what kind of join we want using the how keyword. So if we wanted a left join instead of an inner join, so we wanted to keep all of our Yelp data, we would just say how equals left. And now we see the merged data frame has actually even more rows than the original. That's probably because of the data duplication that I described earlier, where we would get multiple matches for a particular business. But if we only had one match for each business at most, we would have the same number of rows in these two data frames. So this is how we join the columns of different tables together. But we don't always want to join columns together. Sometimes our datasets have the same columns, but they just have data from different time periods or different places. So they're kind of just different sets of rows in the same overlying schema. So for instance, the New York City subway system releases turnstile data every week. So data about how many customers enter and exit the station every week. And that's available here. If you click on one of these links, you can see this is just a big comma-separated value file. So we can download two of these, one for the week of November 11th. Uh-oh. Okay, there it goes. One for the week of November 11th, 2017, one for the week of November 18th, 2017. And these two data sets look, they have all the same columns. They follow the same schema. They just have data from 2 different weeks. And if we want to analyze these weeks together, then we simply want to concatenate the rows together. And we can do that with the pd.concat method. So if I want a data frame for November, or at least 2 weeks of November, I can just concatenate these two data frames together. And if we look at the unique values of date, we now see not only the week up to November 11th, but the week up to November 18th as well. So this is the kind of default or most common use case for concat, but concat can also be used to perform inner and outer joins based on index rather than shared columns. So, for instance, if we perform some data aggregation, so say we want to count the number of businesses in each city. Sorry, since the kernel crashed, I might have to read in several more things. We'll see. So, if we want to count up the number of businesses in each city, we can group our Yelp DF by city, count up the business IDs. Here I'm just naming this series city counts. And if I want to match, I could match up these aggregates by city with the rows of the original data frame if I set the index of the original data frame to also be the city, so that the index of these aggregates will match the index of the original data frame. And then I can concatenate the columns together. So axis equals 1 here. Since I'm not joining concatenating rows, which is axis equals 0, I'm concatenating columns. I put axis equals 1. And I'll say I want to do an inner join. So if I don't have a city in one of these two Pandas objects, then that row will be dropped. So now I have the city counts, the number of businesses in the city for each business. So concat is also a tool for performing joins. And if you read through this documentation, you'll see concat being used to perform quite a few joins, as well as merge. Merge is more commonly used, but concat can do quite a lot of the same things. So that concludes the discussion on joins. We're now about halfway through the lecture. And that also concludes our discussion of pandas. We're going to move on now to a kind of demonstration or like little project or case study, really, of using pandas to work with a kind of messy data set. And working with a messy data set, structuring unstructured data, bringing together different data sources, and kind of the preliminary analysis in data science is often called data munging. So, Wikipedia, the process of transforming and mapping data from one raw data form into another format with the intent of making it more appropriate for a variety of downstream purposes. So it's sort of like engineering your data. Taking data that's raw and unstructured and imposing the structure on it that will make it easy to perform analysis later on. And this might include bringing multiple sources together, as well as imputing missing data, all sorts of operations. So we're going to use Wikipedia and the Pandas read HTML function to scrape data on the top 10 companies in the Fortune Global 500. So there is a page on Wikipedia about this group of companies, the Fortune Global 500. And looking through, you can see there's the top 10 companies for the year. Excuse me, I apologize. Now we can we see that this data is in a table. In the HTML of the web page, so this web pages in general, are represented using a language called HTML, which dictates the layout of the page, how everything will be arranged. And the way this is done is by a hierarchy of what are called tags. So tags are the things in these angle brackets like div, p, h2, h3. So H stands for header, P stands for paragraph. And you can see as I roll over these different tags, on the left, it's highlighting different elements of the page. The Pandas read HTML function looks for table tags. And these table tags usually hold tabular data. And we can see if we continue to scroll over the elements of this table, it has nicely formatted, the tags indicate the structure of the table, the rows and the columns, or the individual cells. So the Pandas read HTML function will look for these table elements and parse the structure of this HTML to read the contents, like petroleum, into the data frame. There's, as you may have seen in the Pandas notebook, an attributes keyword, which can help you specify exactly what table you are looking for on a page. So we can see on this page are quite a few lists. And so if we want a specific table, we can try and isolate that by its attributes, like its class or border or whatever might be here. Sometimes that won't be sufficient. There's not a unique attribute identifying the table. Generally, or always is what I mean, read HTML returns a list. So it's a list of Pandas data frames. So here we got back 5 data frames. And we're just taking the first one, data frame 0, in the list. So here's that data frame, or that table, that we saw on the page. Pandas parsed the HTML and pulled this table into a data frame. And that's a really great convenience function. Scraping websites can often involve quite a bit more work, but since tables have such a rigid structure in HTML, the Pandas read HTML function will most of the time be able to extract tables from web pages. If you want to extract things other than tables, you may have to do more work. So if we split, just to look at what's going on here, okay. Yeah, so we have our data frame. We also have a JSON version of that data. Just a list of dictionaries. Each dictionary corresponds with a row in the table. This is not apparently useful yet, but maybe will be useful in the future. So, this tells us the top 10 companies in the Fortune 500, but there's not a lot of information here. We just have the name of the company, its ranking, total revenue, what industry it's in, and what country it's headquartered in, or where it's incorporated maybe. But if we want to analyze, for instance, how it sits in relation to other companies and its industry, or what fraction of the GDP it makes up, any of these kinds of analyses, we'll need to get more information and join it to this table. So let's bring in some additional data. In this case, we've manually scraped some data from Wikipedia and constructed here a list of dictionaries that gives the number of employees and the year founded for each of the top 10 companies. And this is all available on Wikipedia. We've just kind of skipped the step of scraping and put it directly into a data structure for you. Some of the companies, like State Grid Corporation of China, have a slightly different name than in the other data structure, where we just have State Grid. So we might need to construct a mapping between the two data sets, between the two sets of names. So the Chinese Petrochemical Corporation is in the top 10 Fortune 500 data set called Sinopec Group. State Grid Corporation of China is called State Grid, and so on. So if we want to take these two data structures and combine them, then we would want to perform a join. Match up Walmart with Walmart, State Grid with State Grid Corporation of China. But we can't just join these together quite yet. We'll need to put in a little bit of work. So first of all, we'll need to use our mapping to translate between the names in one data set and the other. And secondly, this list structure is not really optimized for finding matches in the two data sets. So, for instance, if I wanted to join in the employees and year founded for Walmart, and I knew I was going to try and match these things on name, I would first need to find, look at, okay, the first element here is Walmart. Let me find Walmart in the other data structure. And I would need to search this list for Walmart. Now it so happens that it's first in the list, but as we know, searching a list is not very efficient. In this case, since we only have 10 elements, it doesn't really matter, but for larger data sets, it would matter. For instance, in the PW Mini project. So what we would want to do instead is use a dictionary where we could use the name Walmart to look up this information. So we'd want to restructure the other data to have Walmart as a key for this entry. And this resembles what we would want to do in Pandas, where if we were concatenating these things together, the last example I showed with concat, we set the city to be the index, to be the name of the row that we wanted to merge with other rows. So we'll reconstruct other data to allow for lookups by name. So now we have the same exact data structure, well, the same exact data, but now instead of being a list, it's indexed by the names of the companies. And this will allow us to quickly look up by name the information we want to join into the other data. So if we want to compute revenue per employee, all we need to do now is iterate over the Fortune 500 companies, looking up their revenue and using the company name to look up their number of employees and print out the ratio of the two. But again, there's still a lot that stands in our way. We'll need to use the mapping of the names in Fortune 500 to the names in other data. And the revenue is represented as a string, not as a number. So we'll also need to reinterpret these strings into numbers. So to convert the numbers, we'll remove the $, we'll remove the units, and we'll replace that with a multiplication by 1 billion. And we'll return that result as a floating point number. And just to check that this works, we have an assert statement that convert $500 billion is equal to 500 billion, the number. And the very last thing we need to notice, actually, I didn't point this out before, but this mapping is backwards. If I describe iterating over the top 10 and using the names to look up the number of employees and other data. But the value here is the value of the name in the Fortune 500 listing, not in other data. So we actually need to reverse this. So to reverse our mapping, we can just invert the value in the key for each key value pair. And now this is a very important question. What would happen if the mapping was not one-to-one? That is, multiple keys had the same value. What would happen when we do this reversal? Now we can write a function that will compute the revenue per employee. So, given a company from the Fortune 500 company, Fortune 500 list, we can take its name, we can use the inverted mapping to get the matching name for the other data, and we'll use that to get the other data, and we'll get the number of employees. And we save that in a variable called n-employees. And then we'll construct a new key value pair in the company by converting the revenue to a numerical amount and dividing by the number of employees. And then we return the company. Oh no. BP. this changed since the last time I looked at this. BP did not used to be in the top 10. Okay. Well, let's go get the data for British Petroleum. So BP, BP PLC. Other data. They have 74,000 employees. And they were founded in 1908. Okay. And then down here we'll have BP PLC maps to just BP. There we go. So one thing we've been careful to do here is not to mutate our original data. So here is our original data set, the Fortune 500 list, top 10. And here is our data set with the revenue per employee added. And notice in the original that revenue from per employee is not present. We've made a copy. And this can be very important when doing data analysis, because you want your analysis to be easily replicated. And when you mutate your data sources, it's often hard, you often make it difficult to replicate what you did. Because you may be, for instance, maybe there were companies that had 500 million or something, and when you stripped out this word, you didn't check if it was million or billion, you just assumed it was billion. And your $500 million company got recorded as a $500 billion company. And if you mutate your data structure, your data source, then it's going to be hard to ever recover from that error, because you no longer have the original record of what the raw data said. So we've been careful here to not mutate the original data. And we did that by setting up these functions in this way, where we receive a company as input, and that company is like part of the namespace of this function. It only has scope within this function. And so the only mutation we do is here. but it's only mutating that copy that was passed into this function. And then we return that company. And to compute the result, we apply the function in this kind of funny way. So now that we have revenue per employee, we could sort our list of top 10 companies by the revenue per employee. So we'll sort this list. We construct a list of just the company names and revenue per employee. And we're going to sort by revenue per employee using this key function. And this is just saying take each element of the list X and use the second element for the sake of sorting and sort in reverse order. So that's descending order. So now when we sort by revenue per employee instead of total revenue, so here we're sorted by total revenue, we see a very different breakdown of the companies. So Walmart is high in total revenue, but not so high in revenue per employee. And in fact, we see a breakdown largely along industry lines. Energy companies make a lot of money per employee. Likewise, motor companies, automobile manufacturers make quite a bit of money relative per employee relative to retail. So this maybe tells us something about the nature of these industries. Just keeping my eye on the time here. I don't think I'm going to finish this in the next couple minutes. So I'm going to pause here now that we've kind of arrived at our first insight, which was hard fought for. We had to wrangle the data quite a bit. We did, a lot of transformations and rearrangements and had to map names to other names. And at the end of the day, what we learned was different industries seem to have quite different earning capabilities based on their company size. All right, so we'll pick up with this example in the next lecture.